So now that we have some ideas, the basic concepts of vectors, let's take a look at some applications. And you're going to see a whole lot more applications of vectors in your physics courses. I'm just going to give a few brief examples here. Alright, so here we're asked to determine the magnitude of the horizontal and vertical components of a vector m with magnitude m equal to 35 pounds directed at a 50-degree angle from standard position. Alright, so first let's draw this. Let's make sure we got an understanding of what's going on here. Alright, so let me draw some axes. And we have a vector m directed at a 50-degree angle from standard position. Alright, so our standard position, like we learned back, the first few days of class, standard position, a 50-degree angle might look like that. There's a vector, so let me call this the m vector. So there's the m vector, and it is at a 50-degree angle. Now, the basic idea now is, well, this vector has a length 35. The length of that vector is 35, and we're asked to determine the magnitude of the horizontal and vertical components. So now, one way to think about this is that this vector m can be thought of as a horizontal vector and a vertical vector being added together. So if I have this horizontal vector, let me just call it h vector, and I have a vertical vector, let me call it v vector. Basically, the h vector plus the v vector is equal to the m vector. If we think of how we learned how to add vectors, that should seem reasonable. Well, now then we're asked to find the magnitude, right? We're looking for what is so let's find the magnitude of the h vector and the magnitude of the v vector. Well, if we look at this, horizontal and vertical are at right angles. I've built a right triangle here, haven't I? So I've got a right triangle, and so I can use some right triangle trigonometry. I know that, say for example, let's find the magnitude of the h vector first. So then that length, let's see, if we wanted the length of the h vector, then I can use the cosine function. The cosine of 50 degrees would be equal to the magnitude of the h vector divided by 35. And so then the magnitude of the h vector is 35 cosine 50 degrees. Similarly, the sine of 50 degrees would be equal to the magnitude of the v vector over 35. And so then the magnitude of the v vector would be equal to, sorry, that should be a v and it looks like a w. Would be equal to 35 sine 50 degrees. And so now we can just use a calculator at this point. And so if we round to one decimal place, I found that the magnitude of the h vector is 26.8 pounds. We assume it has the same units as the magnitude of the m vector, and then the magnitude of the v vector is 22.5 pounds. And so if we wanted to, now if we think about this in another sense, remembering that the horizontal vector is, the h vector is horizontal and the v vector is vertical, another way to think about this is then that the h vector can be written as the standard vector 26.8 comma 0. Oh, and that should be an angled bracket. And the v vector is then 0, 22.5. So then the m vector, that 35-pound vector, the vector with magnitude 35 pounds directed at a 50-degree angle, could be written as the standard vector 26.8, 22.5. Thinking of that as a sum of the vectors, adding up the components. And in general, we can do this with any vector. If we have a general m vector in standard position, right? With angle theta, then the m vector can be written in the standard vector form as magnitude m cosine theta, magnitude m sine theta. All right, so that's a quick way to take any vector that's thought of geometrically, so at an angle in standard position, and we can then write it as a standard vector by just taking its magnitude and multiplying by cosine theta or sine theta respectively. So let's see another example of that. So now here I've asked you to determine the magnitude of the horizontal and vertical components of the vector r, and I'm telling you that magnitude r is 14 newtons, that's what that n stands for, newtons, shown in the diagram below. All right, now be careful. The way I've drawn this diagram, it's not in standard position. So how would you adjust it to put it in standard position? All right, now would be a great time to pause to try this one out on your own. All right, so while I could work with this 47 degrees as shown in the diagram, and I could think of, I could work with this right triangle, instead what I'm going to do is I'm going to think of it as being in standard position. And so then if I want to think of this vector r as being in standard position, then I need the standard angle. I want that angle theta. Well, that theta would be equal to 180 degrees plus the complement of 47 is 43 degrees, and so that would be 223 degrees. So then the horizontal, right, the horizontal would be this vector. There's the horizontal vector. The vertical vector, here's the vertical vector. And so then the magnitude of the horizontal vector would be equal to 14 cosine 223 degrees. The magnitude of the vertical vector would be 14 sine 223 degrees. And if we calculate those, I don't have these calculated already. Let me use my calculator here, make sure I'm in the correct mode. I need to switch to degree mode. So 14 cosine 223, that is negative 10.2 approximately newtons. And then 14 sine 223 is, hit cosine again, is negative 9.5 approximately. All right, and so then again, if we wanted to think of this angle r, and so kind of putting some ideas together then again, then the r vector is the same as the standard vector, negative 10.2, negative 9.5. And then again, if we could think of this in terms of i's and j's. R is equal to negative 10.2 I vector minus 9.5 j vector. All right, just depending on which system we like to use. Again, it depends on the textbook you use. Some textbooks like the standard vector with the angled brackets. Some textbooks like the i's and j's. It means the same thing. It's just a different way to think about it. Okay, so if you're going to use this idea, you've got to make sure that you're thinking of the angle and being in its standard form, standard position. Okay, so I didn't use the 47. I used the angle from standard position as we've described since almost day one of the course. All right, let's look at another application here. Here we're told a boat capable of 12 knots on still water maintains a westward heading while crossing a river. The river is flowing southward at 4.0 knots. What is the velocity of the boat relative to the river bottom? What is the velocity? Velocity is a vector. We need to find a velocity vector. One thing that you may not be aware of is, if you've never gone boating, is the term knot. Knots describes nautical miles per hour. Okay, so a knot, K-N-O-T, is a nautical mile per hour. And that's slightly different than a traditional mile per hour because we tend to think of most roads as being relatively flat, whereas a nautical mile on the ocean is curved. And so it's slightly different. Okay, anyways, so let's see what's happening here. We've got a boat. A boat is capable of going at 12 miles per hour, 12 nautical miles per hour. But we also have a river that's flowing at 12 knots. Okay, so if we sort of think of, here's the boat, right? What forces are acting on this boat? All right, so in a sense, there's the boat. Think of it as a point in space. And what's happening to the boat? Well, it's being affected by the engine that's taking it westward. All right, so let's call that the E vector. The E vector has magnitude 12. I'll just use K for knots. And then the river is flowing southward. Let's call that the R vector. And we know that the magnitude of the R vector is 4 knots. So now these two vectors are acting on the boat. And so if we think of how we add vectors, the resultant vector of these two, the resultant is going to look, right, if we translate the R vector over, here, there's again the R vector, then the resultant is this vector here. All right, there's the velocity. This is the velocity vector. Now, how do we find that velocity vector? Well, I can think of the E vector as being equal to the standard vector negative 12, 0. It is acting in the westward direction, so that's directly left. And with a magnitude of 12, it must be negative 12 in the x direction and 0 in the y direction. Similarly, the R vector would then be the vector 0, negative 4. The river is acting southward, so in the negative y direction. There is 0 in the x direction. The velocity vector is equal to E vector plus R vector, and then is equal to negative 12, negative 4. Just adding the components of the E and the R vector, since they are now standard vectors. So now what does this mean? Well, what is the velocity? Well, we can think of a couple things. Can we find the magnitude of the velocity vector? Well, sure. The magnitude of the velocity vector would be negative 12 squared, the square root of negative 12 squared plus negative 4 squared. And so that ends up being 144 plus 16. That's the square root of 160, I think. All right, let's see. 144 plus 16 is 160. Let's take the square root of that. So about 12.6 knots. The magnitude of that velocity is 12.6 knots. So if we take the engine and the flow of the river into consideration, the end result is that the boat is traveling at 12.6 knots relative to the river bottom. Now it's also traveling at an angle, and we can figure out this angle. Let's think of this angle right here as this alpha here, and we can figure out that angle alpha. Now again, using some right triangle trigonometry, I can think, well, the tangent of alpha would be the magnitude of the r vector over the magnitude of the e vector. So tangent of alpha is then 4 over 12. And so then alpha would be the inverse tangent of 4/12. And that approximates to 18.4 degrees. Now, one thing that happens when we are talking in a river, when we're in navigation. In navigation, we use a concept called headings. So this is often used in in bodies of water, in the air. Airplanes use a similar idea of a heading, and for headings, we think of due north, as being 0 degrees, and we go clockwise. So due east is 90 degrees, due south is 180 degrees, and due west is 270 degrees. So a little different than our traditional thought. And so since alpha is 18.4 degrees and it is south of west, then our heading might be described as 270 degrees minus 18.4 degrees, 251.6 degrees. So our velocity is, the velocity vector is negative 12, negative 4. What does that mean? It has a magnitude of 12.6 knots, and it's at the heading 251.6 degrees, which is 18.4 degrees south of west. So a slightly different way to think of it when we're talking about navigation. But that's the only situation where we use this understanding of the degrees, right? If we're thinking of navigation and headings, north is 0 degrees, south is 180 degrees, west is 270 degrees. That's what's been built. And so sometimes in these situations, in these contexts, you need to be aware of that system. So here's another example of a problem with a river and a boat. Now would be a good time to pause, try this one out on your own. Alright, so two docks are directly opposite each other on a southward flowing river. A boat pilot wants to go in a straight line from the east dock to the west dock. Alright, so let's say here's the east dock and here's the west dock. With a in a ferry boat with a cruising speed of 8 knots. The river's current is 2.5 knots. What compass heading should the pilot maintain while crossing the river? So if we sort of think, okay, we've got the boat is here right now, and it's, what's happening? There's two vectors. There's the engine, and then there's the river. All right, now the river we know is flowing southward again at 2.5 knots. And we know the boat, the engine, can take it at 8 knots. And if we just sort of think, realistically, the engine is going to have to, if we want to go directly from east to west, then the engine is going to have to take, we're going to have to head out on a vector like this. We're going to have to head out on a vector in that direction, so let's call that the engine vector. And if we call this the river vector, then here's again the river vector. And so then the resultant in this case is the direct path from the east vector to the west vector, and I'll call that the m vector. Now, what I'm going to suggest is, what I've done in a sense is we're going to build some axes here. So let's put the axes right there. There's our coordinate axis system. And so now if we think of the starting point as our 0, 0, then I can think of the E vector, the engine vector, as being at some angle theta. There's some angle theta. So then the E vector I can think of as being the standard vector, magnitude 8, cosine theta. The magnitude is again 8 sine theta. Now the R vector is easier. The R vector would be 0, negative 2.5. Now our resultant vector, which I called M, the M vector, would be the E vector plus the R vector. And so then that would be in standard form, 8 cosine theta, 8 sine theta, minus 2.5. And now if we think about that M vector, if the result is we want to go directly from east to west, we want our M vector to be horizontal. So then this component, the Y component, this must equal 0. So the 8 sine theta minus 2.5 must equal 0. So then the sine theta would equal 2.5 over 8, which means then the theta would be the inverse sine of 2.5 over 8. Now, if we punch this in on a calculator, inverse sine of 2.5 over 8, let's see. That's 18.2 degrees. But that doesn't make any sense. If we think of our theta, if we think of our diagram here, theta is an obtuse angle. So this is incorrect. Theta is instead 180 degrees minus that 18.2 degrees. And 161.8 degrees. That's reasonable, right? That angle theta is an obtuse angle, and we understand how the sine works and how the inverse sine function works. 161.8 degrees is reasonable. So then M, our M vector, fixing that up, would be then 8 cosine 161.8 degrees, comma, 0. So approximately negative 7.6. 0. So our resultant vector, which I called m, is the vector negative 7.6, 0. And so what does that mean? If the river's current is what compass heading? All right, so if this theta is 161.8 degrees, right? If this is 161.8 degrees, well then this angle here, right? This angle, that's the 18.2 degrees. So then the heading, if we remember what we saw on the last slide, the heading would be 180 degrees plus the 18.2 degrees. Remembering, not 180, 270 degrees, sorry, let's fix that. Remembering that due west is 270 degrees, then the heading would be 270 degrees plus 18.2 degrees, that's 288.2 degrees. That's the heading. And the actual speed of the boat relative to the land, all right, the speed would be the magnitude of the m vector, which is 7.6 knots. Let's look at one more example. Here we're told that two people are using ropes to pull on a heavy object. The ropes are connected to the same point on the object. Person 1 can pull with a force of 150 pounds. Person 2 can pull with a force of 100 pounds. If the ropes create an angle of 20 degrees, what is the net force on the object? All right, so we have this heavy object, and we have two things connected, right? We have two ropes connected, and we know that the ropes create an angle of 20 degrees. Well, I can draw, it doesn't say in any particular direction, so what I'm going to do is I'm going to put some conditions on this. I'm going to say, well, here's rope 1. There's rope 1. And I'm going to say that rope 1 is pulling in the horizontal direction. And so then rope 2, here's rope 2. And there's the angle between them at 20 degrees. And I know that the magnitude of R1 is 150 pounds. And I know that the magnitude of R2 is 100 pounds. Now, since I've drawn it like this, again, I can sort of force axes onto this. And so I drew it in a way that made one of the vectors very easy to work with. Notice that R1 now is a horizontal vector. So I can think of R1, the R1 vector, as being the standard vector 150, 0. Since it's in the horizontal direction, and more specifically the positive horizontal direction, then the vector would be 150, 0. Now R2 is a little tougher. R2, the magnitude is 100, but it's at a 20-degree angle. Well, since I've drawn it in standard position, then this becomes 100 cosine 20 degrees, comma 100 sine 20 degrees. And so then if we calculate those, 100 cosine 20 degrees, that is 94.0 approximately. And 34.2. And so I've written the R1 and the R2 in standard form. Now, the net force on these would be R1 plus R2. So let's call that net force, let me call that N. So then the net force would be R1 plus R2. And then that's easy, just adding the vectors. Let's see, 150 plus 94 is 244. And 0 plus 34.2, that's easy, 34.2. So then that's the net force. Now what does it mean? Alright, so I've built this net force, N, and it looks like this. Right, our net force is, I don't know, maybe something like this. There's the N vector, where the horizontal component is 244 and the vertical component is 34.2. Well, then I can easily find the magnitude. What's the magnitude of that net force? Well, that would be the square root of 244 squared plus 34.2 squared. Uh, 246 approximately pounds. And then another thing we might want to consider is, well, what angle? Right, so if we had those two, we know that originally those two ropes were pulling 20 degrees apart. What's the resultant angle? So let's call this angle here, let's call this alpha. And we could easily use a tangent function now. And we know then that the tangent of alpha is 34.2 over 244. So then alpha would be the tangent inverse of that. And we can approximate that. It's about 8 degrees. So that angle alpha is 8 degrees, and so what that means is, and if we kind of go back to our original diagram, what that means is, here's the resultant. Here, I'm going to try and draw the n. Right, so in purple, that's the n vector, and the angle theta, it's at approximately an 8 degree angle with respect to the R1 vector. So the angle between the R1 vector and the n vector is approximately 8 degrees. All right, so these are just a few examples of how we can use vectors in slightly realistic situations, maybe not completely realistic at this point, but you do a lot more with understanding how to use vectors in your physics courses. So I hope this gives you just a taste of what to expect in those courses. All right, have a good one.